Plenty of time. There we go. All right, so today we are going to talk about causal inference, and I've kind of alluded to causal inference throughout our discussion of study design and everything else, but today we're actually going to talk about what we mean by causal inference. Who wants to take a stab at what we mean by causal inference? Anyone? Yeah.
Associating a cause to an outcome.
Yeah, so like actually saying that something causes the disease. So up until this point, we've really just been talking about, is an exposure associated with an outcome? Right? Is a risk factor associated with a particular disease? But we haven't really addressed the fact as to whether or not our risk factor or exposure actually causes the outcome we're interested in. So today we're going to talk about what types of criteria you really have to meet in order to be able to say that A causes B, not just that A is associated with B. So when we're doing epidemiologic study, we start with our descriptives, right? We start with our descriptive studies. We know how the disease is distributed in the population, which helps us form our hypotheses about that. Then we start to look at our correlational studies, which are what we've really been talking about up to this point. Our case control studies, our cross-sectional studies, our cohort studies, to look and see if the exposure and the disease are associated with each other. So, who here has heard the phrase, correlation does not equal causation? Who here knows what that phrase means? Who wants to tell me what that phrase means?
Well, correlation is just like if one present, then the other one might be present, or if one is increasing, if one variable is increasing, the other might be increasing, but that doesn't necessarily mean that it happens because the other one is.
Yes, exactly. No, that's exactly right. So it means that variable A and variable B, if variable A increases, variable B increases, or if variable A decreases, variable B increases. So the two are associated with each other, but that does not mean that variable A caused variable B. It just means that there are related going on. Now we're getting to the question where we want to know, is the association causal? So we've established that an exposure and a disease turn up together. They're associated with each other. Now we want to know, okay, does our exposure really cause our outcome? But there are certain criteria we have to meet in order to establish that. So just like we were saying before, when we're talking about associations, it just means that there's some way they go together. It could mean that as variable A increases, variable B increases. It could variable A increases, variable B decreases. But it means that there's some sort of relationship between those two variables. Now, causal inference is the process of deriving cause and effect conclusions. So we're drawing these conclusions about cause and effect by reasoning from our knowledge of factual evidence. So we generally don't have just one study that helps us determine that something is causally related to another. What we usually have is a compilation of evidence. We have a whole bunch of studies, and taken together, all of that information allows us to make a causal statement. And this is just a fun little cartoon. And most of you, I'm sure, notice in the news that every other day it seems like somebody's coming out with some information that contradicts the other, right? So it used to be you always put your baby to bed on their stomach because they were scared that your kid was going to vomit and aspirate. And then they realized, wait, everybody putting their baby to bed on their stomach increases the risk of SIDS, so put everybody to bed on their back. And it's just like this long thing, right? But so as we gather more evidence, things change. We change recommendations. But this is just a fun little cartoon that's kind of like, spin the wheel, and whatever your exposure is associated with your outcome. I don't know. You probably can't read it very well. You would probably read it better yourself. I thought it was very funny. You don't have to. You don't have to think it's funny at all, but it is very funny. I'm telling you. All right. So, when people first started talking about causal associations, they were really talking about, does a single thing cause another thing? So they were really talking about back when infectious disease when infectious disease was the most frequent cause of death, and infectious disease was really becoming prominent, we found out about germ theory, and we started understanding that an organism could cause an illness. And back in that point, we had the single cause, the Henle-Koch postulates. So, the Henle-Koch postulates for a single causal factor, you have to have the organism present in every case of disease. So if you're talking about HIV, or if you're talking about AIDS, HIV has to be present in every single case of AIDS. The organism can be isolated and grown in pure culture. So if I take a person that has AIDS and I take a blood sample, I can then grow HIV in culture. The organism must, when inoculated into a susceptible animal, produce specific disease. So if I take that HIV that I have grown in culture and inject it into a monkey, I think monkeys are susceptible to HIV, then the monkey would develop AIDS. And then the organism must be observed in and recovered from the inoculation. So then I take a blood sample from the monkey, and I can put that blood sample back in culture, and I can grow HIV again. So this is the full cycle. So this really corresponds only to when we're talking about infectious diseases. But this is, does our germ that we found, does the bacteria that we found, the virus found, does it cause the disease that we think it causes? Has to meet this criteria. Now, yes?
Is this like current? Is this still used?
Not really.
Seems like a lot of things that wouldn't have to fall into that category.
You're absolutely right. So this was kind of the origination of causal thinking. So when people first started to come up with the idea that we have to really establish that one thing is actually causing another, this is what they came up with. And this was really talking about, it was back in the era when chronic diseases were not really prevalent because everybody died by the time they were 40. And when it was really infectious disease, that was the problem. And these hold most of the time for infectious disease. Now, generally speaking, most infectious diseases are also multifactorial. There's other things, not sure they can cause, but there's other components that are related to whether or not you get the disease. But generally speaking, if you're talking about infection, this is the postulates that you have to meet, but it's not, this isn't really the criteria that we use today. This was, when we first started talking about causal thinking, this is what people were talking about. The problem is that most of the diseases we talk about today are multifactorial. They have multiple things that can cause them, and more than one thing can cause the same disease, right? But before we get to that, we're going to talk about sufficient causes and necessary causes. A sufficient cause means that that exposure alone will cause the disease. You don't need anything else included. A sufficient cause alone is enough to produce the disease. A necessary cause means that the disease or outcome cannot manifest unless that exposure is present. A cause can be necessary but not sufficient. So you can have a cause that has to be there in order for the disease to develop or the outcome to develop, but it won't, in and of itself, that exposure won't cause the disease to develop. It has to be there in conjunction with some other things. So sufficient, the exposure definitely is by itself can cause the disease. Necessary, that exposure has to be there for the disease to develop, but it has to be there, but it doesn't have to be the only thing that's there. It just has to be there. You may need something else to make the disease manifest. So, most of the time, especially when we're talking about chronic diseases, one exposure or risk factor alone is not enough to cause the development of disease. Usually, it's multifactorial. There are multiple component causes that all work together to then cause you to have the disease. This is definitely the case in almost all chronic conditions. I'm not going to say all of them, but most of them. Let's see. A sufficient cause doesn't have to be one factor. It can be multifactorial. So you may have to have A, B, and C all occur in order to get the disease. Let's look at this kind of graphically. I think it makes it a little bit better. So, in these three pictures, we have A, B, C, D, E, F, and G. All of those are individual risk factors, or individual exposures. They are all component causes for disease X. And And this particular component cause A is the only necessary cause. So if you don't have component cause A, if you don't have that exposure, you will not get this disease. Will not happen. Now, A by itself is not enough to give you the disease. So A is necessary. You have to have it. But A must occur in combination with B, C, D, E, F, and G, in some combination of that, in order for you to get the disease. Right? Yes.
So sufficient cause doesn't really ever happen? Or
It does. So let's say if you, get tuberculosis, right? So somebody that has tuberculosis comes and spits in your face.
so that would be
The germs are enough to give you the disease. You just need to have.
Okay.
Now, that's not talking about the fact that, in general speaking, if we're talking about environmental factors, you're more likely to get tuberculosis if you're living in chronic conditions, right? Because of that. But yes, the TB, bacilli, whatever, is enough to actually give you tuberculosis. It is a sufficient cause.
Okay.
So there are 4 types of causal relationships. The first, your exposure can be both necessary and sufficient. So if it's necessary and sufficient, the disease will only occur if the factor is present, and the exposure will always lead to the disease. This doesn't happen that often, just like we were talking about. So it can be necessary and sufficient.
Can you repeat that?
Yes, I can. So if a factor is necessary and sufficient, having that factor present, it's the only thing you need to have in order to develop the disease. And if that factor is present, you definitely will develop the disease. It can be necessary but not sufficient. That's what we were talking about a second ago. If it's necessary but not sufficient, the factor must be present for the disease to manifest, but that factor alone will not cause the disease to manifest. It works with other component causes. A factor can be sufficient but not necessary, meaning that just having that exposure alone can cause the disease. However, you don't have to have that exposure to get the disease. There are other things that can cause it as well. So, an example, vitamin B12 deficiency can cause anemia, but there's other things that can cause anemia as well, right? So B12 deficiency alone is a sufficient cause for anemia. But you don't have to have B12 deficiency in order to get anemia. There are other things that can cause it. And then a factor can be neither sufficient nor necessary, meaning that specific factor can combine with other factors to cause the disease, but you don't have to have that factor, and that factor alone will not cause the disease. This is actually the most common thing we see, right? So, being overweight in and of itself does not give you diabetes. There are other ways to get diabetes besides just being overweight. But being overweight in combination with other factors is a risk factor for diabetes. It is a component cause, right? Yeah.
Can you repeat the definition for that one?
For neither sufficient nor necessary, it means if it doesn't have to be sufficient, meaning the disease, you can't get the disease just from having that exposure. And then if it's not necessary, that means it doesn't actually have to be there for you to get the disease anyway.
That doesn't.
Right. So it's neither sufficient nor necessary. Yeah.
So, are there like a genetic predisposition for diabetes, where it says you can't produce insulin?
Mm-hmm.
So that would be sufficient but not necessary for diabetes?
The genetic predisposition wouldn't necessarily mean that you develop it unless you had a genetic marker that actually.
Yeah.
Yes. So that would be
sufficient but not necessary.
yes, because there are other ways for people to get diabetes. Yes. All right. So there's 4 types of factors that we can really talk about that play a part in the causation of disease. So predisposing factors are those that make a person more susceptible to the disease. These are things like age or sex, or it could be prior illness or certain genetic traits. They make you more likely to get the disease. They make you more susceptible to the disease. Enabling factors are external factors that may contribute to the development of disease. So these are things like being low income, or having poor nutrition, or unsafe housing, other socioeconomic factors. These are external to you, but they can contribute to you getting the disease. So the tuberculosis example, for instance, if you live in really crowded conditions, that enables the transmission of tuberculosis. Precipitating factors are those factors that are associated with the onset of disease. For example, exposure to a specific pathogen or a specific harmful substance. So asbestos exposure is a precipitating factor for mesothelioma, which we all know because we've all seen those lawsuit commercials that are still going on. And then finally, reinforcing factors are those factors that can aggravate an established disease. So like if you have repeated exposures to poor environmental conditions. Yes?
Oh, okay.
Mm-hmm. So all of these we can term all of these risk factors, right? In the broadest sense. So a risk factor is any factor that's positive, or that's not positive, that's associated with the development of a disease. So the risk factor, the term risk factor is a broad term for anything that's associated with the development of a disease. We can break it down into these specific types, but just because something is a risk factor doesn't mean it causes the disease. Doesn't even necessarily mean it's a component causes the disease, though it might be. So how do we tease all this out? If there's multiple causes to disease, and we can't conduct randomized controlled trials on every single risk factor we're interested in to control for all the other stuff to see if a particular risk factor actually causes the disease, what do we do? Well, Sir Bradford Hill was nice enough to come up with some criteria for causal inference. And I'm sure you've heard me say the word temporality over and over again. I think I say it at least 5 or 6 times every single time we have class. Because it's important. Because temporality means that the cause precedes the effect. So if you cannot establish that your risk factor took place before the outcome developed, you cannot say that two things are causally related. We'll go through all of these individually and talk about what each of them mean. But so we can say time or temporal sequence, but it simply means that your risk factor, your exposure of interest, precedes the outcome in time. And not just by like a day. It precedes the outcome in enough time, that in a reasonable amount of time that the disease could manifest, that could really happen. So if I can't say I smoke 1 cigarette today and I develop lung cancer tomorrow, I probably can't say that that cigarette that I smoked today caused the lung cancer that I developed tomorrow, right? It has to be sufficient amount of time between the exposure and the outcome, and it has to be a sufficient amount of time of the exposure depending on what it is. But you have to be able to demonstrate that your exposure preceded the outcome. All right, strength of the association. So we have the risk ratio and the odds ratio. Those are the measures that we've been looking at as measures of association. The stronger the association that you see, the more likely it is that the exposure, disease relationship is causal. That does not mean that there wasn't a compounding factor that confused it. So just because you have a strong relationship, does not mean that your exposure caused your outcome. But the stronger the relationship, the larger your risk ratio, the larger your odds ratio, the more likely it is that there is a real causal relationship there. Because the less likely it is that that relationship is entirely due to confounding. Another point, just because a relationship is weak doesn't mean that it's not causal. So these are guidelines. Yeah.
Can you give me a whole of that?
Of a weak relationship?
Because my inclination is to kind of give that data the boot.
Well, so there are other reasons that you might be seeing your weak relationship. Part of it might just be because of the way the study was designed. Part of it might have been because you didn't give people enough of a dose of the exposure. Right, so you could have an exposure that caused the outcome, but if people just got a little bit. So if you're worried that some toxin in the air caused lung disease, but the people that you're studying had one breath of it, they might not have had enough exposure to actually cause the disease. So you would have seen a weak relationship there, but that doesn't necessarily mean that it's not causing it. But the stronger the association that you see, the larger the risk ratio, the odds ratio, the more likely it is that that relationship's not going to disappear when you control for confounding. All right, dose-response relationship. This is why I was so excited when you guys, which group was it that broke it down by differing doses? Because if you can demonstrate that the strength of association increases the more of a dose somebody receives, you have strong causal evidence, right? So the more cigarettes a person smokes, the more likely they are to get lung cancer. It's called the dose-response relationship. Now, you won't always see this. Some things have just a threshold effect. So if it has a threshold effect, you're exposed, nothing happens, and then all of a sudden you hit that threshold of exposure, and now you'll get the disease, right? So you wouldn't see a dose-response relationship in that particular instance. But, like the other criteria, if you can demonstrate this happening, you can demonstrate the more of this drug you get, the more likely you are to get better, that's strong evidence that the drug is causing you to get better. Simply means that you keep coming to the same conclusion based on different studies. So a ton of different researchers have studied this particular research question, and they've done it using a bunch of different study designs, and everybody keeps getting the same answer. That strongly supports that there's a causal relationship. Basically, because each different study has different types of bias that are associated with it. So if you can show that you keep seeing the same relationship, regardless of the study design, you've been able to say, okay, we've controlled for different types of bias in each of these different study designs. And regardless of which type of bias might have been at play, we still keep finding the same answer. That's strong evidence that there's a causal association. Biologic plausibility means that there are known or postulated biological mechanisms that explain your exposure-disease relation. We have some good reason for thinking that what happens is happening. Now, biologic plausibility is more important when you're talking about medical things and less important when you're talking about psychological and social things that you could be studying, right? Because you may not have a biological mechanism for why self-esteem causes people to gain weight, or low self-esteem causes people to gain weight or something, right? If that's your hypothesis. So that may not be something where you have a biological plausibility. But this does transfer, you should still have a good theory as to why something's happening. But if the results you find make sense in the context of what is known in science in the greater scheme, the stronger your ability to say that we probably think this association is causal. Reversibility. This simply means that if you take the exposure away, that then you find a reduced risk of disease. So when the exposure is present, you have an increased risk. If those people that were at an increased risk, you take the exposure away, now they're no longer at an increased risk, they're at a decreased risk. You have stronger support that the exposure causes the disease. So remember when we talked about last week the crossover designs, where you had two treatment groups, and treatment group 1 was given drug A, and treatment group B was given drug B, and then you stopped and you switched them. You switched the treatment group. That helps you demonstrate reversibility. So you took the drug, you're giving someone treatment, drug A, and their blood pressure goes down. And you take drug A away and their blood pressure goes back up, you have a lot more evidence that drug A is causing a decrease in blood pressure, right? Now, reversibility is not something easily demonstrated when you're talking about behavioral interventions.
Like reversibility also be like negative? is sometimes, because then like what if you're like become dependent upon a drug to get like a desired effect rather than just helping people reach that naturally. So like with like beta blockers and like blood pressure, once you start taking them, it's kind of like you're dependent on them. the rest
Yes,
of your
well,
life.
so that's why none of these are hard and fast criteria, right? So it's like, the more of these that you kind of meet, the better. But things can be causally related without meeting all of these criteria. The only criteria that you absolutely have to establish is temporality. The rest of them are just suggestions that we would like to see, but are not always going to be the case because depending, so reversibility also if you have a behavioral intervention, right? You're trying to increase someone's self-esteem. I don't know why that keeps coming to mind. So you're trying to increase someone's self-esteem and you give them this behavioral intervention. You can take the intervention away, but they probably still are maintaining some effects of that intervention, and so they're not going to plummet. Their self-esteem is not going to plummet just because you took it away. So in interventions like that, your intervention still could have caused their self-esteem to get better, but we're not going to be able to demonstrate that causal relationship through reversibility. So this is one of the criteria, and so part of it is you have to understand what you're studying and understand which of these criteria are most appropriate based on what you're studying. All right, and then finally we have study design. So we kind of alluded to this earlier, but different study designs provide stronger or weaker evidence. So we've talked about kind of experimental studies being deemed the gold standard of study designs, the best types of study designs. Basically that's because they're highly controlled, right? So we know we can establish the temporal sequence of events. We know we have done our best to control for other factors. And so in experimental study design, we can be more confident that what we're doing, that our intervention caused the outcome. So you will see large, huge trials or whatever, where people at the end of an experimental study say, I have established causality. And that's not necessarily an incorrect statement. But you still want to be careful because experimental designs, like all study designs, are susceptible to different types of bias. Cohort studies are the next kind of strongest study design, mainly because cohort studies still allow us to establish the temporal sequence, right, of events. Case control studies are kind of next in line. They're more susceptible to certain types of biases, and they don't allow us to establish the temporal sequence. And then we have cross-sectional and ecological studies. We've kind of talked about all of those as we've gone on. But the stronger your study design, the more confident you can be about saying that this relationship might be causal. And this is just a little kind of fun picture of what we could possibly see as hierarchy of experimental evidence. All right. So that is the entirety of the lecture for today. Do you guys want me to record the review session on integrity?
Yes.
Okay. I didn't prepare any slides or anything for the review session. Here, actually, I'm going to pause this. I'm going to hand out the review. So I told you earlier there's the folder on Blackboard that has 2 different review sheets. One of them is kind of a template with questions like what is epidemiology, what are populations, and then the other one I think is just a list of terms and potential questions.
They both have the same material.
For the most part, yeah. There may be one term on one sheet that's not on the other, but if you get the big stuff, you'll be fine. Like I said before, this is a student-directed. Oh, there was one thing I wanted to address based on your homework. Now that I remember, wanted to talk about case control and cohort studies, kind of like how we really are defining case control and cohort. What is the one big thing that makes a cohort study a cohort study?
Study individuals from a group, like a shared characteristic.
Be more specific.
We get a pick what the characteristic is.
You're dancing around it.
Isn't it like you divided the 2 groups, like exposure and exposed?
Yes, we start with an exposed group. What's the second component? That's really important. So we're starting with an exposed group, but what's the really important thing about that exposed group?
that they've never had the disease before?
Yes, that the entire group that we're studying is non-diseased. So when we have a cohort study, regardless if it's prospective or retrospective, the group that we're starting with is non-diseased. Both the exposed and unexposed, no one should be sick. Now that doesn't mean they don't have a cold, that means that they don't have the disease we're interested in, right? But so when we're talking about a cohort study, yeah.
You just toss them out if they do.
Yeah, so that'll be part of your inclusion or exclusion criteria. So whenever you start a study, you'll decide who exactly you want to be included in your study, just like you guys did in your example thing. So who are out of those people that meet your inclusion criteria, one of the exclusion criteria would be that they have the disease you're interested in. You can't be sick. If you're starting with a cohort study, they're a non-diseased group of people, and then you have the exposed and the non-exposed. Then you follow them and see who develops the disease. Now, anybody want to take a stab as why they have to be non-diseased?
Because you're trying to get the relationship between the exposure and the disease. So if they're already diseased before, right, then you can't really link.
Right, because in the cohort study, you want to be able to establish that the cause occurred before the effect. You want to be able to establish that the exposure occurred before the outcome. And you can't do that if people already have the outcome at the start of the study. Now, a case control study, who are we starting with? Diseased people, yes. We're starting with cases of disease. And then we find people that don't have the disease to serve as controls. And when we're doing a case control study, we get people into our study regardless of what their exposure status was. We don't want to know when we start our study. We have the diseased people that are our cases. We find a comparable group of non-diseased people that are controls, and at that point, after we have those people in our study, then we can go back and assess whether or not they were exposed to what we were interested in. So is that clear, like who we're starting with at the beginning of a study? And in a cross-sectional study, we just ask everybody everything at the same time. I send out a survey and I say, hey, do you have this disease? Hey, were you exposed to this risk factor? You answer all of it, and I look back to see if they were associated. Right?
So that one's pretty hard to be like legitimate evidence sometimes.
So it's one of the weaker study designs for establishing the causal relationships that we were talking about. Yes, because you cannot in any way say that the exposure occurs before the disease. You can't really, you're not really controlling, I mean, you can statistically control for a number of other factors, but it's not as controlled as if you have a case control study where you found these cases of disease and then you look for the same source population to find the controls, right? Because the point of a control group in the case control study is to find the baseline exposure in the population. And in a cross-sectional study, you're just saying, hey, everybody come on in, fill out my survey. Give me some answers. And then I'm just going to look to see if anything falls together. So the distinction between those three basic study designs is very, very important. Now, obviously, in the real world, the designs get more complex, but those are the three main observational study designs that we use in analytic epidemiology. Now, let's go back up. For experimental studies, what makes a study an experimental study? What do you have to have in order for it to be an experimental study?
You have to have manipulation, you have to have randomization of people.
Yes, so the people have to be randomly assigned, random assignment, randomly assigned to treatment groups, and the investigator has to manipulate the independent variable. The investigator manipulates the exposure. And those two things have to be present for it to be an experimental design. All right. So that's the big important things that were jumping out at me when I was looking at your homework the past couple of weeks. What do you guys want to talk about? Dance around everything, but I would like to help you review concepts. Yes?
Can you go over the basic calculations? When the odds ratio is used versus
Yes.
risk ratio.
Yes, so we calculate an odds ratio for case control studies. We actually also use it for cross-sectional studies. When we're doing it for a cross-sectional study, we call it a prevalence odds ratio. I don't think I ever used that phrase. You don't need to know that phrase, but that in general you run across it that way. But so we can calculate an odds ratio for case control and cross-sectional studies. What we have is their chalk here. There are little bitty, tiny, yucky pieces of chalk. Anyway, so for an odds ratio, we have a 2x2 table. And we always have our disease on the top. And our exposure on the side. And now I'm not positive that I'm right about that. My brain has stopped functioning. Am I right?
Yeah.
I am. It's like, wait a minute. Alright, so for an odds ratio, we're talking about the odds. So the odds are the number of people who have the disease in the exposed group divided by the number of people who have the disease in the unexposed group. So it's A divided by C over B divided by D. Yeah?
So when do you do like A over A plus C?
That is when you're talking about the risk ratio.
Okay.
So wait, that wouldn't be A over, it's A over A plus B.
Oh.
So we're talking, right here we're talking about the odds of exposure given that we know you have the disease divided by the odds of exposure given that we know you do not have the disease. So we're talking about disease columns, and because we're talking about odds, we're not adding anything. So we go back to probability theory, which you may or may not care about. Odds are the number of successes divided by the number of failures. So the disease in the exposed population we consider success,
So
and the disease in the unexposed is the failure.
so is that still considered like? Because we have to know what a proportion is, right? So is that still considered a proportion then?
Mm-hmm.
Is the proportion?
Mm-mm.
Does
No, these are odds.
Okay.
A proportion would be the proportion of people that were exposed in the diseased group would be A over A plus C. That would be the proportion. But when we're talking about odds, we're not talking about proportion. We're talking about the odds of exposure in the disease group divided by the odds of exposure in the non-disease group. So if I asked you, find the odds of the exposure in the diseased group, I have not asked you for a ratio. I have asked you for the odds of the exposure in the disease group, which would just be A divided by C. When I ask you for the ratio, that means you're comparing one group to another. So that would be the odds of exposure in the disease group compared to the odds of exposure in the non-disease group. So when you're writing out what this means, you always want to write out blank compared to blank, right? So you want to say, if we're talking about smoking and lung cancer, we're talking about the odds of smoking given that we know you have lung cancer. So the odds of exposure, the smoking exposure, given that we know you have lung cancer, are 5 times more likely than the odds of smoking given that we know you do not have lung cancer. So you know what is compared to what. Now, this equation you can simplify to AD over BC. That's easier to remember. That's the way I always remember it. That's just if you rearrange the math. So conceptual way, easy to remember way, you'll get the same answer regardless. That's the way the math works. Because math is fun. Alright, so that's the odds ratio. So when do we use an odds ratio? Case control and cross-sectional, right? So for a cohort study, we use the risk ratio. Because in a cohort study, since we've established the temporal sequence, we can also establish we're actually talking about risk, because risk is referring to incidence of disease. So if we go back and we're talking about the risk ratio, our table's set up the same way. Our table doesn't change. We always want disease on the top and exposure on the side. But now we're talking about the risk ratio is the incidence of disease in the exposed population compared to the incidence of disease in the unexposed population. or the incidence rate, sorry. Actually, it's the cumulative incidence, let's be really precise. It's the cumulative incidence in the exposed population to the cumulative incidence in the unexposed population. And we'll go back around to the difference between cumulative incidence and incidence rate in a second. So when we're talking about the risk ratio, we want to know, we're talking about the cumulative incidence in the exposed. So we want to know, given that we know you're exposed, it's A, in this case, divided by A plus B. Because it's now the proportion of people that are diseased within the exposed group. Yeah. So we have A divided by A plus B over what? C divided by C plus D. Exactly. Because now we're looking at the number of people that have the disease given that we know that they were not exposed. So our risk ratio is the ratio of the people that are diseased given that we know they're exposed compared to the risk of having disease given that we know you are not exposed. Now, we interpret the magnitude of those associations the same way. So if you get a risk ratio of 1 or an odds ratio of 1, it means there's no association, right? Because that means that you have a 1-to-1 ratio. So the same number of people got sick in both the exposed and the unexposed group. You have an odds ratio of 2, we're getting a little bit bigger. Now, the odds ratio, remember we interpreted it the odds of exposure given that you have disease. So we interpreted it as the odds of smoking given that we knew you had lung cancer. When we're talking about the risk ratio, we're talking about risk of disease. So we can say the risk of getting lung cancer is 5 times greater in people that smoke compared to the people that don't smoke. Because we started with the exposure in our study design.
Can you do an example of that too? Because I know you said the way we worded it was like kind of different than the way we looked at it right away. Like the way you would say it right away when you looked at it.
The wording, I'll give you some examples, but the wording itself is not as important as what you say is what you're talking about, the risk of what or the odds of what. So whenever you're talking about your odds ratio, you always want to say the odds of having the exposure are blank times in the diseased group compared to the non-diseased group. So the odds of smoking are 5 times greater in people with lung cancer compared to people without lung cancer. When we're talking about risk ratio, it's the risk of having the disease is greater in the exposed compared to the unexposed. So the risk of having lung cancer is greater in people that smoked compared to people who didn't smoke. When we're talking about a cohort study, and we're talking about risk ratios. And I will give you some caveats on those interpretations after your exam to avoid confusion. So are we good with the risk ratio and the odds ratio for the most part?
So when you describing a risk ratio, you have to say the risk of getting, or the risk of...
The risk of developing disease blank is greater in the people with the exposure compared to the people without the exposure.
Okay.
Let's backtrack a little bit back to this cumulative incidence rate, incidence prevalence, all those things we talked about like the first, second week of class that probably leaked out by now and you're going to have to stuff back in there. What is incidence? The number of new cases of disease. So incidence itself is really just a count. The number of new cases of disease. Now when we speak of incidence, we're typically either talking about cumulative incidence or we're talking about incidence rate. Now, if you'll recall, back when we talked about, or back in the beginning, we talked about fixed cohorts and dynamic cohorts. What is a fixed cohort?
The fixed cohort, like the group doesn't change from the year.
attended.
Exactly.
The other one is people are not.
Exactly. So in a dynamic cohort, people enter the cohort during the study and they leave, and then they come back, and then they leave, or they don't necessarily come back. But like new people come in, some people go out. The denominator changes. That's the one where we're using person time. Is that ringing a bell? Idea of person time? Because we count our denominator is the amount of time contributed by each person over the course of the study. When we have a dynamic cohort and we're using person time, we calculate the incidence rate. Because we're talking about the number of new cases over a certain amount of person time. That's our denominator, the incidence rate. Cumulative incidence refers to a fixed cohort. So in a fixed cohort, everyone that starts is there at the end and nobody moves in and out. The same people the whole way through. So cumulative incidence is just simply the number of new cases of disease over everybody that was in the study.
Can you repeat that last part?
Yes, so cumulative incidence is the number of new cases of disease just over the total number of people that were in the study. Because the same number of people getting at the end and throughout the whole way. It didn't change. So for ease of interpretation and for the purposes of this class, when we're talking about analyzing cohort studies, we're talking about use ratio in the context of a fixed cohort. Now, because that's the easy one to calculate. So that's what we're doing. Yeah.
So does the dynamic cohort, does that go with that, what you were talking about earlier, how you said that you assume that people were there the whole time?
So that was talking about intention to treat analysis and experimental study design. And that's dealing, so it's a similar idea. Yeah, so when you have an experimental study design, you're probably going to lose some people along the way. And you have to assume that those people just continued on with whatever treatment group that they started with and analyze them as such.
So you still analyze them? You know,
Well, you do, but not using, there's more sophisticated statistical methods that allow you to deal with loss to follow-up.
okay.
So you can deal with just the amount of time people contributed to the study, but that's way beyond the scope of this class. And I don't like to use that excuse, but I'm not sure how to talk about it without getting into it, and then that would just be... So if you really are interested, sit down and I can go through all of it with you. I'd be more than happy to sponge the brilliance of survival analysis. Bless you. But, I have 2 little chihuahuas, and they're much louder than that.
That's kind of like
But I used to have people that brought their dogs to class.
Really?
Really?
Yeah. Back like when I was doing my master's degree, there were a couple people that would bring their like giant golden retrievers to class. And they weren't even treating them to be service dogs. I don't know. Anyway, total off the point. But all right, so dynamic cohort, people move in and out. We calculate person time. We're talking about incidence rate. Fixed cohort, everybody's there throughout the whole thing. It's the same people. We're talking about cumulative incidence in that context. Right? You good with those for the most part? What else would you like to talk about?
How many questions are on that?
I don't remember.
What's the format of it as well?
It's mainly multiple choice and then some short answer.
How long do you
I think there might be some matching too.
How long do you think it will take us?
I have no idea because I had people complete it in 20 minutes and I've had people take the entire time. So depends on how well you study.
It'll be here? Or
Yes.
online?
No, it's here. It is here.
Is it going to be on paper or?
It is going to be on paper. I am going to print out pieces of paper. You are going to need a pencil or pen to complete this. I'm considering at some point moving it online and just having you guys take it at home. Then I can have an extra week of class, but not this year. Yeah.
Our finals take home though.
The final is take home.
is actually a question yet. What's different about phase 4 trials?
So phase 4 trials are post-marketing studies. So that means that the drug has gone through everything that it needs to go through for whatever specific indication they're trying to get it approved for. The FDA has said, yes, you can use this drug. And then doctors start prescribing it. And now we go back and we track through all the secondary database. So when people have severe adverse events to drugs or things like that, the doctors usually report it back. And so now we have all this data that's existing, and in a phase 4 trial, we're analyzing that data to see if now all of a sudden we're seeing side effects or bad things happening that we didn't see in a smaller phase 3 trial. But it's post-marketing, and it's technically not a clinical trial. It gets housed under that in the FDA research site, but we're not really putting people into study groups and looking at them. We're doing it observationally, but we're not randomizing people. You look like you almost have a question. Is it just not formed, or?
No.
Okay. You're just.
I was thinking about asking one, but I already know I have the answer somewhere. I can find it.
Well, maybe other people don't have the answer, so you should ask it anyway.
Okay. I was just wondering, I was gonna just a reminder on how you do positive predictive value and negative predictive value if you want to use like the ABC.
Yes, sensitivity and specificity, my favorite topics. Truly they are. All right, so when we're doing sensitivity and specificity, what are those establishing? What do we use those for? Anybody remember that?
Screening.
Yes, and we're talking about screening tests, but we're specifically looking for some aspects. So we talk about the reliability of the test and the validity of a test. So are we getting the answer that we think we're getting? Are we getting to the truth, right? So when we do sensitivity and specificity, instead of disease and exposure in our 2x2 table, we now have the gold standard up here. And now we have whatever our new test is. And so this box right here are the true positives. These are the people that tested positive using our new test and that were deemed to have the disease based on our gold standard. So these are the true positives. B are the people that our screening test said were positive, but that our gold standard said were negative. So these are our false positives. C are the people that our screening test said were negative, but that our gold standard were positive. So what are these?
False negatives.
False negatives. And so these would be true negatives, right? The people that the gold standard said were negative and that our screening test said were negative. So when we're looking at our sensitivity, what is sensitivity?
How might that R positive be actually test positive?
Yes. This, I think, who was talking about the A over A plus C? That's what you were referring to.
Yeah.
Okay, yeah. So sensitivity are the proportion of people that tested positive, or that tested positive that truly were positive, out of everybody who truly is positive. Yeah, sorry. It's the number of people that tested positive divided by everybody that truly does have the disease. So we can write it as A over A plus C, or we can write it over as the number of true positives over the number of true positives plus false negatives. But either way, it's the proportion of people that our test said were positive out of everybody that's truly positive. Yeah?
Isn't it the other way around? It's the proportion of people who are truly positive out of everyone who tested positive?
No.
No?
That's positive predictive value. Yeah, so that's the positive predictive value.
Okay.
So the positive predictive value is the number of people that tested positive that are truly positive out of everyone that tested positive. So our specificity, so our sensitivity, we're trying to find how good is our test at identifying the people that have the disease out of everyone who truly has the disease. And specificity is how good is our test at screening out the people that don't have the disease out of everyone who truly doesn't have the disease. So our specificity is our true negatives. The number of people who truly don't have the disease that tested as if they didn't have the disease over everyone who truly doesn't have the disease. Or we can say true negatives over the true negatives plus false positives. Huh? So our sensitivity is telling us how good our test is at determining who has the disease out of everybody that has the disease. The proportion of people that our test said had the disease out of everyone the gold standard has said have the disease. And our specificity, how good are we at identifying the people that don't have the disease? Right? How good is our test at picking out those people that truly aren't sick and saying that they're not sick? Sensitivity and specificity are functions of the test. They do not change based on the prevalence of the disease in the population. That's not the case for positive and negative predictive value. Positive and negative predictive value are dependent upon the prevalence of the condition in the population. Which is why we want to give screening tests to people in high prevalence populations. Because if you give a screening test, even if it has excellent sensitivity and specificity, if you give it to a population that doesn't have very many people that have the disease, if you have a high sensitivity test and you give it to a population with a low prevalence, you're going to get a lot of false positives. And that's going to cost a lot of extra money for a lot of extra testing, right? Because when we're talking about screening tests, we're not talking about diagnosing the disease. We are talking about taking people that are not symptomatic and trying to identify this disease before it becomes symptomatic, right? Now, we use sensitivity and specificity when we're talking about diagnostic tests as well, but for the purposes of this class, we're really using it in the context of screening. What's up? Just talking about me.
I'll just take a piece right now.
Making fun of me? I get it. It's okay. All right. Anything else? Email me with any questions if you think of anything. Please let me know and I will answer it as best I can, as quickly as I can. Did everybody, so I know Blake and Vera had to run away to their thing. So just make sure there should be 15 people in each group. I am assuming that you guys can count. Is that a correct assumption? My 4-year-old can count. So actually, my 19-month-old can count to 4. She's very excited. My kids like math like me. We're in math.
You guys can't count.
Eagles are.